Conditional probabilities are simply probabilities that depend on other events. We will refer to this table 4.42, where we have data showing the number of wins recorded by two friends who were playing tennis against each other based on the length of time they warmed up before the match. So we have the warm-up time, it is short, long. Then we have the probability or the chances that Deborah wins, Bob wins, and the totals that we have. So the first question is asking us to find the probability that Deborah wins the next match if only she has a short time to warm up. So you can make your own key to say A can be probability that Deborah wins. B can be probability for short time. But preferably I'd rather use the letters that are within here. Short should be S, long should be L. Deborah should be D, and Bob should be B. So here what it's asking for is a probability that what? Deborah wins if, when you get the word if, just know that that is where the potential probability is. Altogether, if has a short warm-up. So here it is Deborah given S. So D given S. So the S will come down, then D intersection S. So D intersection S is simply where D and S are meeting. That is 4 over the grand total, 4 over what? The 50. Then probability that you have a short time, it is 10 over 50. So it's 10 over 50. So this and this will cancel. It will still remain with 4 over 10, which gives us what? 0.4. Or 0.4 here. I could as well tell you to say Deborah given short. You go where they meet Deborah and short. That is 4. But the total for short is 10. That is a direct way of calculating it to give you 0.4. So part B, so this is our 0.4 that we're getting it. Now part B, we're being asked to find, assuming Deborah won, describe the likelihood that the warm-up was short. So as where the word assuming is, that's where you put this letter down. So here is assuming Deborah won, find the probability that the warm-up was short. So here we're looking at probability of what? Deborah short given Deborah. Try to calculate this. I'll give you a minute on this table.
Collins, it's still 0.4, isn't it? Hello? Collins?
Yes.
It's
So
0.4?
I need to, where do they meet? S given D, they meet at what?
At 4.
At 4, but the total for what?
4 win. Okay.
Is what? Well,
Okay.
what are we getting as total? 0.2.
Okay.
So if the question says if Bob won, what's the probability that the warm-up was long? Long warm-up. So where the if, the letter that precedes if is one that will go down. So if Bob won, what's the probability that the warm-up was long? So you're going to say if Bob calculates the probability that the warm-up was long. So what are we going to do here? Why do they meet long and Bob?
24.
24, correct.
Oh,
But the total for what?
long.
Long. The bottom guy, the total for what? Bob. Which is
Oh,
so always ensure that this shortcut is only functional as you follow this prescription. All right. So let's look at the following up questions. So we're being asked, assuming the warm-up was long, what's the probability that Bob wins? So where the word is assuming, meaning the weight which is assumed, it comes down. Assuming long, so assuming long, find Bob. Find Bob. Okay. If you had the word if, warm-up was long, so meaning if the warm-up was long, find Bob. So you need to understand the grammar behind there. So assuming we have B given L, what becomes all together. So Bob given long, where do they meet Bob and long? 24. But the total for what? The total for?
For long is 40.
40. Are you getting it? Trying to make it as simple as can be. So this is how you go about it. You need to understand and appreciate this probability. You must also appreciate axioms of probability. Remember, probability of A given B, what comes down? Probability of B. On top, what do you have? A intersection B. All right. If you have probability of B given A, what comes down? Probability of A. On top, you have A intersection B. Now together. Then when you cross multiply, you discover that probability of what? A given B, you multiply times the probability of B. What do you get? The intersection of A and B. You cross multiply here, probability of B given A, you multiply it by the multiplicand here. What are you going to have? Probability of A. So you need to understand that as long as the multiplicand kisses the conditional probability down there, you get an intersection. If there's B there, there should be B automatically there. So it will help you think in a very fast way. Now, let me teach you how to elaborate or simplify the tree diagrams. Suppose we're told that the probability of A is 0.4, probability of B is 0.6, probability of A given D is 0.10, and probability of B given D is maybe 0.04. So we want to find three things only. Number one, the probability of D. Number two, the probability of the reciprocal of this A given. So A given D, we are going to have what? D given what? A. Then A, we're going to have probability of D given what? B. These ones are carrying 3 marks each. So I use two cardinal methods. Number one, there's what we call the probability table. Probability table starts like this. You are going to have the prior probability. The original probability must always add up to what? 1. So here probability of A is what? 0.4. Probability of B is what? 0.6. Are they adding up to 1? Yes. It should always add up to 1. Getting 1 there. Then we go to the conditional probability, which says A given D. All right. In fact, this is supposed to be probability of A. It can be that it's supposed to be coming from A. So it's probability of what? D effective coming from A. Effective coming from B. Then here the opposite, A given that was effective, B given that was effective. So here, what is the probability of the conditional probability? So we are told that this is a conditional probability here, the column for conditional probability. So this is probability of what? D coming from A. What's the probability? 0. What? 0.10. And here the probability of D coming from B is what? 0.04. So when I multiply these two columns, 0.10 and 0.04, what we're going to get is what? The intersection. We must ensure that this one is the same as the initial. This one is the same as the initial. So intersection, what intersection are we going to get between these two? It will be A intersection D. So when we apply these two, we're going to get 0.04. Then when we apply these two, we're going to have D intersection what? B. This by that, it is 0.024. So it's just the intersection that you get whenever I'm applying the conditional probability. To intersect is to multiply. Now there's what we call theorem 2. Whenever you're adding two intersections, you consider the common letter that is there. So D intersection A and D intersection B. What common letter do we have? D. So 0.064. That is the probability of D. So 3 marks here, you're quoting a probability of D, which is 0.064. Then the last part is called the posterior probability. Whenever you're dividing an intersection, for instance, probability of D intersection A, okay, divided by probability of D. The letter that is down is the letter that will be down in the conditional probability. So here D will come down there. So the other letter, there are obviously two letters, so A will come up. So divide A intersection D intersection A over D, this would be A given D. How about A D intersection B over D? What would be this conditional probability? What will come down? Probability of D. So on top, it's obviously other letter. There are only two letters B. So in this case, we're going to have 0.04 divided by 0.04 divided by 0.064. What do we get? 0.625. Then here is 0.024 over 0.064. What do we get? 0.375. So this total must always come up to 1 as well. That is how this is supposed to be done. Are you together? This is how it's supposed to be done. Now, how does a question come in an exam setup? So that very question we are from doing is an exam type of a question. So I want us to illustrate that question the way we can apply it. Any questions so far, first of all, before I proceed? So conditional probability is tough in this version, but you just need to understand. So let's go through another mini example. Suppose that the probability of X is 0.2, probability of D even coming from X, 0.4. Probability of Y is 0.8. Probability of D coming from Y is 0.1. So they're asking us to find three things: probability of a defective, probability of X given defective, probability of Y given defective. So let's come up with the table again. I said we have a prior probability here, conditional probability here, we have the intersection here. We have what? The prior probability is X, which was 0.2. Make sure that the prior probability always adds up to 1. Probability of the other Y is 0.8. So the total is giving us what? 1.0. The conditional probability here is D coming from where? X. Probability here is D coming from where? Y. So this one was giving us what? 0.4. And this one is giving us 0.1. When we multiply this, we get the intersection. So this will be D intersection X. This will be D intersection what? Y. When we apply these two, this is 0.08. Apply this is also 0.08. So when you total up here, common letter is probability of D, which is 0.16. Then we finally go to the posterior probability. Who wants to help? How do we handle the posterior probability? When you divide the probability of D intersection X over probability of D, what are we going to get? We're going to get probability of what? X given D. So this would be 0.08 divided by 0.16, which is 0.5 or 50%. Again here, probability of what? D intersection Y. If we divide it by the probability of what? D. What we're going to get is D will be down there. And here we're going to have Y. So in this case, we're going to have 0.08 over 0.16, which is 50%. So I want you to get used to the pattern for you to understand what is still yet to come. Are we together so far? Together so far?
Yes.
So let's look at an exam question that came. So here we have, in a certain town, males and females are 50% of the population. So probability of a male is what? 50. Probability of a female is what? 50. Put together on that one. Then we are told that it is known that 20% of the males and 5% of the females are unemployed. So we're going to say males who are unemployed coming from unemployed. No. Unemployed coming from the males is what? 20%, so 0.2. Then unemployed, it should come from the probability. Unemployed coming from the what? Females is what percent? 5%, 0.05. All together in interpreting or narrating this so far. So let's draw our table together. So we have prior probability. We have what? Conditional probability. We have what? Intersection,
intersect,
we have what? Posterior.
still,
So what is our probability? Probability of M is what? 0.5. Probability of female is what? 0.5. These one together. Then the conditional probability was what? Unemployed coming from the males was 0.2. Unemployed coming from the females was what? 0.2. Unemployed coming from the males 0.05. So when we multiply these two, here we're going to get what? Males intersection unemployed. These are males who are unemployed. So when we multiply this one by that one, is 0.10. Multiply these two, it is females intersection unemployed. So when we multiply these two, we get 0.025. So in total up there, the common letter is letter U. So this is a probability of the unemployed, which is 0.125. So when I divide M intersection U over U, it will be what? M given U. When I divide F intersection U over U, it will be what? Probability of F given U. So what is 0.10 divided by 0.125? You're getting 80% or 0.8. Because I know this will add up to 1, even if I don't calculate that one, I should know automatically that this is 0.2. So the question is asking, what is the probability that the person was unemployed given the way male? So males were unemployed. So this is 80%, so 0.8. And what is the probability that the person was employed? Forget the probability that it was a female. So female given that's unemployed was 0.2. 6 marks, 6 marks. So this was total of what? 12 marks. So here it's my people perish because of what? Lack of knowledge. Standing. Doesn't it look easier now? Are we moving together?
not easier, but it's making sense.
All right, you just need to tell your mind that this is going to be doable. All right, let me go back to another one here where we're given 3 machines. There's X, Y, and Z. These 3 machines have equal capacity. So meaning, since there are 3, each one has a probability of 1/3. If there are 4, it is a quarter. So probability of X is 1/3. Probability of Y is 1/3. Probability of Z is 1/3. The total is 3/3, which is 1. That's a probability. So sometimes probability will not be given. You just need to understand the grammar there. But they have equal probability. If there were 2, it would be 50-50. If there were 3, the 3.33. But there, don't leave it as a decimal because it will affect the answer somehow. So 1/3, 1/3. If there are 4, 1/4, 1/4. All together. Then we are told that it is known that percentages of defective X, Y, and Z are 2, 7, and 12%. So conditional of what? Defective coming from X, 2%, so 0.02. Probability defective coming from Y is 7%, 0.07. Probability defective coming from Z, 12%, 0.12. All together so far? From conditional, we got what? Intersection. So when we apply these two, what are we going to have there? X intersection what? Intersections D. About here, when we apply these two, it will be Y intersection what? D. About here, it will be what? Z intersection what? D. All together. So 102 divided by 3. We get what? 0.0067. 0067. And here again, 0.07 divided by 3. We get 0.0233. 0.233. And this one, 0.12 divided by 3. We get 0.04. What we're interested in here is a total phase to get the probability of a defective. So plus 0.023 plus 0.0067. The total will be 0.0697. That is a defective. Fortunately, the examiner would always want to assess one of them. Suppose, what is the probability? Suppose an item was randomly selected, it was found defective. What's the probability that it was produced by Y? So what they're asking you is the posterior for Y here. So just divide this over the D. So what they're asking for is Y given what? T. So what's the probability for Y? 0.023. And what is our D here? 0.0697. So you're going to divide 0.023 divided by the answer we had there. So your final answer will be what? 32.99. 32,998 or 999. So these are things that most of you fear because you don't really take time to want to digest. Are we together so far? I really want this to look as easier as it should be. Right. So can you try one on your own? Which one can I choose here? 5, 6, 7, 8. Choose any. That I can do for you. Just choose one. 5, 6, 7, 8. Which one? Let's try this one here. Question number 7. So we are told that 20% of the employees in a company are graduates. And of these, 70% have supervisory position. Of those who do not attend college, 20% have supervisory positions. Okay, so question is, what is the probability that the randomly selected supervisor is a college graduate? So let's digest this in a simplified manner possible. Let's digest this in a simplified manner possible. What are we given here? Step by step. Anyone to try? Let's extract the data. Just the first key you need to have is just data extraction. You can make your own key if you like. Let's extract the data. Yes, Messi, what data do we have from there? Okay, so the probability of college graduate is what? 20%. So we're going to say probability of college graduate is 0.2. So meaning probability of not being a college graduate, you can just say complement of college graduate is what? 0.8. Do we agree? What else are we told? Supervisor given college graduate, or a supervisor coming from the college graduate is what? 75%. So supervisor coming from college graduate is what? 75%. All together. Same thing we're doing, just that you need to know how to extract the data. So what they are now asking us is to find the probability that it was a graduate given that they're a supervisor. So they want us to find the probability of the opposite. Okay. So college graduate, it's a graduate. Supervisor coming from the graduate. Now they're asking us, what's the probability that the random selected supervisor is a college graduate? So graduate, given that they're a supervisor. How do we expand this? Probability of graduate intersection what? Supervisor divided by probability of a supervisor. This question was not really easy in the sense that you needed to think very well. Okay, so we have extracted the probability that the graduate 20%, not a graduate 80%. Supervisor given graduate 75%. So we need to also find the probability that of a supervisor only. So the probability that a person was a supervisor and a college graduate is going to be found by finding the intersection of these two. Okay. Probability of a graduate times probability of supervisor given graduate. When we multiply these two, we're going to get the probability of a supervisor and means intersection. Probability of supervisor and a college graduate. So let's do this. Probability of G times probability of S given G is going to be equal to, I said, whenever these two are kissing or multiplying, we're going to get an intersection. This is S intersection G. Also, probability of G is 0.2. Also, probability of S given G, 0.75. So when we apply these two, we're going to get the probability of what? S intersection G. So 0.2 times 0.75, we're going to get 0.15. So this is the probability of what? S intersection G. Now, we're interested in finding the probability of S. So we also need to find the probability of G. What's the probability of okay, so far before I proceed, are we together? So far together? So we're given another parameter here of 20%. This is a probability that of those who did not attend college, the probability that their supervisors is 20%. So this one is probability. How do we read that notation? Those who did not attend college. So it is supervisor given did not attend college. So probability of supervisor given did not attend college is 20%, 0.20. So what do I multiply these two to get an intersection? Multiply probability of supervisor times probability of not attending college. So I say this bottom guy should is. So this is what? G complement. So we have this one of 20%. The probability that did not attend college was what? 80%, 0.18. So this is going to give us 0.16. Now remember, this is a probability of S intersection what? G complement. What we're interested in is to find an S there. So theorem 2 is what we're getting to. So we have what? S intersection G plus S intersection G complement. So if we total up these two, what we're going to get is the common letter throughout. What is the common letter throughout? Probability of S. So probability of S is 0.15 times 0.16. So we're going to get 0.31. So we add these two, 0.15 plus 0.16, we're going to get 0.31, which is the probability of what? S. So now we can go to our question here. We say G intersection H. We already calculated our G intersection H. What is our G intersection S? It's the same as S intersection G. So we found this one as 0.15. So here we put 0.15. And that's the probability of our S. We just calculated it as 0.31. So when we compute these two, 0.15 divided by 0.31, we're going to get 0.48. Okay. So this is how we do it. This is how we do it. And also use a table for this one, if you like. I know people get tired of probability because it has its own complexity. Let me go to our table, hoping that it will simplify issues. So in this table, where we said the first column is what? Probability. So we have probability of what? 20% are graduates. So graduates are what? 20%. So 0.2. Meaning those who are not graduates are what? 80%. 0.8. All together. And we got a conditional probability. So supervisors who are coming from a graduate. How many are they? 70%. So of these, 75% of supervisors, okay, are in supervisory position. So 75%. So supervisor coming from graduates, 75%, 0.75. And we're also told that supervisors who do not attend graduates, so not graduated, are 20%, so 0.20. And we go to the intersection. So this one will be what? Supervisor intersection graduate. This one, supervisor who did not graduate. So here we're going to have what? This one times that one, 0.15. This one times that one, 0.16. When you total up, the common letter is what? S. So the total number of the supervisors we have in total are 0.31. Like I said, the examiner will always ask for one element. What's the probability that the supervisor is randomly selected who is a graduate? So they're looking for the posterior for graduates, the opposite. We divide. So this will be what? G given S. So it's simply dividing 0.15 over 0.31. So this is now when you appreciate the table that it is much easier. So 0.15 divided by 0.31, which is 0.48. Are you agreeing with me that the table is far easier? Gladys? Okay. So we can proceed. So that is on the probabilities. Now we can look at question number 9. Question number 9. So I keep echoing the fact that you need to be familiar with the what? The axioms of probability. To say probability of A given B is given by A intersection B over what? B down there. If we're given B given A, what goes down? We have A intersection B divided by the probability of A. Right. Then A intersection B is produced by cross multiplying there. This is A given B multiplied by the what? The multiplicand, which is B here. Again, here, if I cross multiply here, A intersection B will be what? Probability of B given A. This is Bayes' theorem times A. All together. So this is our song for probability. So we also have the union set formula, faithful formula. It doesn't change. Unite is to add. Probability of A intersection A union B is probability of A plus probability of B minus the intersection of A and B. So it so follows that when this one comes this side, we can also have an intersection set A intersection B, which is equal to probability of A plus probability of B minus the intersection of A and the union set of A and B. What we just did is manipulated this following formula. This guy comes there, this guy, they just swap positions. Then finally, we have theorem 2, which simply says that whenever you are adding intersections, A intersection B plus A intersection B complement, you pick the common letter throughout. Which letter is common throughout? A is common throughout. So B and B complement are not the same, so we qualify the A. So here, on the second thought, if you're given A intersection B plus A intersection B, this time if we put the complement on the other letter, maybe A this time. So which letter is common throughout? Letter B. So this is what we call theorem 1. Theorem 2. Of course, we know the complement of A is when we subtract 1 from A itself. So if A is 20%, the complement of A should be what? If A is 20%, complement of A is 80%. And like one, if B complement is 1 minus B itself, so the two must add up to 1 short. Probability of A plus its complement must give us what? 1. So if A is 20%, the complement of A must be what? 80%. So this is all you need to know for the question I'm about to take you through. So we have an insurer who offers 2 types of policies, home and car insurance. So I told 70% of all customers have a home insurance. So probability of H is what? 20%, so 0.7. Notice I told that 80% have a car insurance. So probability of a car insurance is 80%, so 0.8. So the following question follows up. Every customer has at least one of the 2. So when you combine C union H, it should be 1 or 100%. So part A, what's the probability that the customer does not have a car insurance? What are they looking for? Does not have a car insurance, the complement of a car. Who can help us find the complement of a car? Is 1 minus car insurance. So our car insurance is 80%. So 1 minus 80% is 0.2. At B, what is the probability that a customer has a car insurance and their home insurance? The word "and" means what? Intersection. Car intersection home. So here we can extrapolate this formula for the union set, which will have a union set. So when these ones swap, the intersection will be A and B, then subtract the union set. So in this case here, to be probability of C and H. Subtract the what? The union set. So probability of H was 0.7, probability of C was 0.8, and when you unite them, we get at least one has both. So 0.7 plus 0.8 minus 1, we get 0.5. So that is intersection. Then part C has home insurance given car. Probability of home given what? Car. So what goes down there? Car. On top we have what? Home intersection car. Remember, this is base theory. So just from calculating H intersection C is the same as C intersection H. So 0.5, then probability of C is 0.8. So we divide 5 divided by 0.8. So we get 0.625. And finally, probability that does not have a car given. So probability does not have a car given home insurance. So already whenever there's a complement somewhere, we have theorem 2. So C complement intersection H over the probability of what? H. H is not a problem to find because we already have it. That's a probability of H, 0.7. Then C complement intersection H. So whenever the complement is on this letter, just make the other letter subject. So since the complement was on C, make H subject using theorem 2. Remember I said if you have two intersections, H intersection C, H intersection C, the complement should be on the other letter. If there's H there, the complement should be on C. So what's the probability of H? 0.7. What's the probability of the complement on C? We don't know. But what's the probability of H intersection C? We're just from calculating it here. H intersection C is intersection H, which is 0.5. So this is plus. So 0.5. And it goes this other side, we're going to have the probability of what? C complement intersection H will be 0.7 minus 0.5, which is 0.2. So the complement is on C. So this is what we're looking for here, where the complement is on C. So we put 0.2 and divide 0.2 divided by 0.7. We're going to get 0.286. 0.286. So this is how we tackle that question. So we end here for now. Unless there are any burning questions, you can ask.